are the wine tank safety, and we develop comms. My name is Branchaus.
I'm Alejandra Perez.
I'm Juliana Pistola.
I'm Philip Joe.
I'm Carlos Flores.
So what is comms? Comms is carbon dioxide oxygen monitoring system. It is a low-cost, low-power air monitoring system that can be used in any situation that requires air monitoring, such as in wine tanks or mines. So why would you need comms? There are many deaths every year due to carbon dioxide poisoning. One case is a 22-year-old in France died when falling into a wine tank because of the levels of CO2. CO2 is a CO2 is a non-visible gas, and you cannot smell it, and you will not notice it's poisoning until it's already too late. It can go from mild dizziness to death. So this is why comms is required to keep people alive, especially in those that are cleaning wine tanks after fermentation. So overall, this system monitors carbon dioxide and oxygen levels and warns workers when these levels have approached dangerous levels. Currently, it's a buzzer system, and it will automatically buzz as soon as the levels hit for carbon dioxide above 5,000 parts per million, and for oxygen 2,000 parts per million. Initially the system starts off asleep. Every 2 minutes it will wake up and take the sensor reading. If the reading is toxic, it will automatically do a buzzer notification to alert the workers to leave. After that, if required, it can store the data and send it wirelessly through XBees, or if needed, any other sort of data storage. And then it will reset itself to go back to sleep and come back on again every 2 minutes. This will allow for in a regular 8-hour day, workers are continuously notified when levels are dangerous to evacuate.
So this is the 3D rendering. This is for the CO2 sensor, and then here we have alpha. We have the PSOC, the 4200. We have a step up, and we have a step down. And we have the JSD and the USB and some passives and the battery charging. Here's the bottom view. This one, the blue one, is the O2 sensor, and the black one is our buzzer. And here's a lateral view of it. So this is how we're planning on connecting the CO2 sensor with our alpha, and those pins over there are actually going to be connected to the pins over here.
And here's some information about the battery and the battery charger that we used. So we have the operating supply current, supply voltage, the output voltage, and the output current. I also added the current parameters that we chose through the setup of the actual schematic of our battery charger. So we set the charging current to 200 milliamps, the termination 24 milliamps, and the limiting current at 500 milliamps. And there's also some basic information about the lithium-ion battery that we used.
And so this is our regulator. We're getting an input of 3.7 from the battery charger, and then we have the output 3.3 that will power the PSOC, and we will also power the XV.
Just a small little notification. Originally, we were using the adjustable regulator chip, which required those resistor capacitors. We have then now switched to the fixed version, and we can just tie the feedback straight to the output. So that will be the change.
And here's some information about the step-down converter and the step-up. For the output voltage of the step-down, we chose the 3.3 voltage layout, and that will power the XP and the step up, we just put the range that's given on the data sheet, and the actual output voltage that our layout will give is 5 volts, and that will power the sensors.
And then here's the step up. So we get our input from the battery charger, and then the output will go to the sensors. And yeah, so this is like the most recent update. Originally we had like a 2.2 inductor, but we switched that. So yeah, that's probably the main switch we did.
So this is our piece of digital communication series. So piece of 4200, but with the specific model, has 2 SCB blocks and 2 USB blocks. We're using all of them. We are using UART for the oxygen sensor and a UART for the XV Wireless model, and we are using I2C for the carbon dioxide sensor. This is another sketch of the piece of digital.
Okay, so this is the carbon dioxide sensor we decided to go with for our alpha design. We went with the K30 carbon dioxide sensor. It measures CO2 concentrations up to 10,000 parts per million, which is more than enough for what we need. It does require a warm-up time of up to 60 seconds every time you power up the device. There's a response time of up to 20 seconds via diffusion of gas. The sensor operates at voltages between 4.5 to 14 volts, so there's a wide range of voltages. For our purposes, we only need 5 volts due to the step-up converter. Current consumption is low, 22 milliamps, while during active measurements, and then it spikes to 100 milliamps every 2 seconds for approximately 120 milliseconds to power the IR lamp while the sensor is measuring. So at 5 volts, power consumption is about 200 milliwatts. And so to save power on the sensor, well, the voltage regulator will be the converter will be disabled every 2 minutes after a measurement is gathered to save power. And this is the oxygen sensor we went with, the Luminox optical oxygen sensor. It measures up to 25% oxygen concentration. Has a response time of up to 30 seconds. It operates as a voltage of 4.5 to 5.5 volts. Again, 5 volts required for our CO2 sensor. Current consumption is very low, 7.5 milliamps during active measurements. And so at 5 volts, power consumption during is about 37.5 milliwatts. And again, to save power, we'll do the same thing with the CO2 sensor where we disable the voltage, the boost converter.
So in beta, our goal is to have the actual alert part working. So add the buzzer and have it, once the readings are reach toxic levels, turn on. The buzzer works off a square wave, so we'll have to make that. To improve power consumption, we'll also be implementing sleep mode. So this will be turning off all the regulators that aren't needed, shutting down the PSOC as low as we possibly can to minimize current consumption. We'll also be changing from the K30 to the Cozier. The Cozier has only about a 3 millisecond response time, so it doesn't need to be on as long, while ours, we've talked to the tech support of the company, and they said that it needs to be on for the full 1 minute before it can give an accurate reading. So to avoid having it basically on throughout the whole time, we're switching to the Cozier. It also requires less current. I think it's around 60 milliamps, while ours can peak up to 100. Questions? And we do have a video.
Okay.
So the video is demoing with this setup with the red proto board. It has the oxygen sensor and the K30.
See, so is it on both?
One
Alpha
The
test.
final one, this is final.
Final, this one.
This is a demonstration for the Team Alpha 1 tank safety. We have our carbon dioxide and oxygen sensors working right now. Our sampling rate is 1 second. On the left-hand side, we have the carbon dioxide graph measuring in parts per million. And on the right-hand side, we have the oxygen graph measuring in millibars. And now we will blow on the sensors to show that they're working correctly. And as you can see, the carbon dioxide level rises drastically as the oxygen concentration decreases drastically. And after a few seconds, they should level out eventually.
Okay, so we got the question slides.
Okay. Was that you breathing into it or something?
Yes.
Okay.
So when you breathe into it, the CO2 goes up,
Yeah.
and since the oxygen has less oxygen, it goes down. It's more carbon dioxide.
Okay, good. That was really good.